but maybe a portable one. Thank you. Good morning or good afternoon, whatever. Thank you. I should like to talk about small portable electric energy producing reactor, and we should like so-called mass produce it to give it to people who are interested in LNR in general. Should be cheap and reliable. When I got here this morning, I just caught the last sentences by Lynn and Alan Smith that somehow we should attract attention, funding, and interest to LNR in general. And in my opinion and in my experience, if you show people something that it is working and useful and potentially giving something to the society, it's an attraction itself. So we don't have to give a certain reward. You remember Mark Twain wrote Tom Sawyer's Adventures of Tom Sawyer, when Tom Sawyer sold the right to paint the fence. And he got rich because all his friends wanted to paint the fence. So I think if we are able to give people something simple and they can start with, it will be an attraction itself. The very idea came from Dave Nagel. He gave me the idea some years ago that this field should produce small study reactors. Because if people can have hands-on experience with a study reactor, they see themselves that this is working, then the objections of patent office and so on is no longer of interest. That's a personal opinion. So I should like to talk how we are at this moment with this development, and we are on the same line as Lutz Jadner and Bob Grenier volunteers. That's the only way. It's a volunteer-based adventure. So this is, as I see fusion, the hot that is non-catalytic. We are familiar with it, that the costs are in the billions of euros or US dollars, while catalytic, I prefer this expression catalytic because catalytic processes makes these processes so-called cold or low energy. So in my opinion, catalysis is a little bit nearer to the physical reality because low energy is just a vague term. So it's a better. There are a number of approaches and very exciting approaches I heard during the last 30 years. The most well-known, of course, the phonon as a catalytic agent in the Pons-Fleischmann direction, then cavitation, usually in water or oil, and dust as a solid dust as a transmutation agent or catalytic agent. But now I'm talking about the red column, which is based on condensed plasmoid, and this Lutz Jadner baptized it as condensed plasmoid, and I see this is the most fitting expression so far. There were other names. All discoverers gave their own name, but condensed plasmoid fits the best. That was, and we are using it, of course, for this reason. So, what are the principles of catalytic fusion? I have hands-on experience on both cases. When solid, usually carbon particles are in the order of micrometers, and there are two mechanisms. One, when a proton is attracted to a highly charged by electrons, trapped electrons, protons are hitting the dust particles, so neutrons are created. That is one reaction path. That's a personal opinion. And the other is when the Coulomb barrier is overcome between two positive ions. But there is another one when the same task is done by a condensed plasmoid, which has a large negative charge. In fact, a nearly forgotten German researcher, Hans Raeder, discovered it just before the Second World War, and it is a tragedy. And he repeated the same tragedy because before the First World War, British scientists at the London College were doing beautiful transmutation experiment, sparking in hydrogen. So history repeats itself. However, I found another source of inspiration, lots of forgotten inventions. All mad garage inventors are sparking in their garage because it's cheap, and sometimes they stumbled into something remarkable. So not everybody is mad who is working in his garage. That's conclusion. So very crude layout and graphics. No. I'm always troubled. This is Lin's device. Yes. So this is the general layout. It's a relaxation oscillator, and you see a very simple discharge tube, but there are tricks. Later I will tell you how to make this discharge tube. It's not simple, not straightforward. There are some wizardry. And in this device, sometimes we use neon tubes because we are unable to capture most of the energy generated during the diffusion process. So we use a nanoporous surface, a semiconductor, homemade, and it requires technology, patience, trial and error, and because we want to give a over-unity device to interested parties, for us, engineering efficiency is important. Efficiency. Otherwise, if, let's say, I would say if the COP is 0.1, but it is an interesting academic adventure, few people would be interested. But if the COP is above 1 or around 2, it might attract already interested people, especially when we know that this COP of 2 is a gross underestimation. It's a very conservative. So lots of energy is escaping. What we have to deliver, something continuous operation, very cheap fuel that is hydrogen, water, vapor mixture. And one attraction of this method would be a very good power per weight. This could be reduced by weight tremendously. So there is lots of possibility. So I think even electric airplanes are possible to make this way. We found not more than 6 months of tube lifetime, then we ruined it. It's easy to ruin because we gave samples to Guido Parchi, and they nearly always destroy the semiconductor surface. So it requires a certain skill like driving a car. You have to be used to it, or even learning how to use the bicycle. In principle, on the long term, it would be easy to reprocess because only the surface which is of interest, and the electrodes are inexpensive aluminum oxide. And you see again the simple circuit. What we use here as simple relax oscillator. The tubes are coaxial cylinders, and the load is usually an ohmic resistance and the capacitor. When we were at the early, very, very early days of this R&D process, Jean-Paul visited us. He saw the crudest, the earliest devices. We are intending to produce two types. One is the compact one, this long one. We use it because it's high voltage, I mean up to 2 kilovolts, and we should like to protect our customers. But we set up an idea, a criteria that the device should be able to pull apart and reassemble. And this tube type of construction failed. After the 5th assembly and reassembly, some mechanical problems always cropped up. So we are facing different problems than most of the field here because most people who do experiments, it's more or less academic. We are facing practical problems, how to assemble and disassemble the device. And this flat kind of version is more or less meant for people who really want to do experiments, who want to take apart, change parts, change reactor tubes, and so on. So it's more or less a flexible tool. These are the units under assembly. These pictures were made 2 weeks ago. I called my colleagues, and these tube types will be ready next week, hopefully. And this flat type still requires some time because we shall provide these water splitters, and we use Chinese peristaltic pumps. And they didn't, they just arrived when I left. So why we think that spark-based, condensed plasmoid-based device is LANR? Because we have lots of transmutation data. Unfortunately, most of the volunteers who are working with us lazy, really. They are unable to keep a decent test log. They just go in, switch on, let's give them frequency and voltage, and usually they fuck up the system immediately. But we have lots of transmutation data. When we start the experiment, let me show you. It's aluminum oxide, pure. There is nothing else on the surface, just aluminum oxide. But when they use wet air, all kind of other materials crop up. I talked on previous conference, we always find lots of carbon and of course sulfur and calcium sometimes. And in one spot, let me show you, we found tungsten. On one spot only, a tungsten. So why? We were discussing that usually these extra elements are found in isolated spots. They are not covering the whole surface, just isolated spots. But I have shown on previous conferences traces of carbon when the discharge moved along the perimeter. So it's always there. This is the easiest when somebody buys and uses this experiment and has access to EDX, they will find it. This is the this is the tungsten spot. These are other from other parts of the cathode. Again, the usual carbon here, sometimes copper, and other elements like phosphor. In my opinion, phosphor is coming from the fusion of oxygen and nitrogen, and sulfur is oxygen and oxygen. And plus, you need some neutrons, extra neutrons. These are the traces, what the discharges on the oscilloscope. And the energy balance test, the methods were given at Szczecin by Sebastian Domoslai. And there is another independent method that we are able to charge and discharge the capacitors. We know the frequency, and it is easy to calculate with a plus minus 20% error, of course, because the discharge is wobbling. The input and the output measurement is dissipated on resistors, because the output is, of course, electricity and electromagnetic radiation. And these are the calorimeter measurement and how the bottom of the calorimeter looks like when it is not yet filled with heat-conducting resin. So these are the output resistors too, and this is the bottom of the thermometer. It's an alcohol thermometer, not mercury. Okay. And these calibrations are made with DC at different temperatures. As we increase the temperatures, we increase the power, so it's easy to calibrate. We have a number of problems. The first and the worst is the quality control. Second, reactor tube construction, and the input-output electric circuit design. Quality control A. So we found that transmutation happens only with a special type of surface. You see here, this is a nanoporous surface. If we have this honeycomb structure, then it works. If we are unable to do it during the semiconductor process, then it doesn't work. So why sometimes products of very heavy, sometimes only lighter elements? My assumption is that it depends on the size distribution of condensed plasmoid. if we were able to produce only small size condensed plasmoid, which is able to do nothing else but, let's say, to fuse hydrogen only to deuterium or tritium, that would be the ideal, because we could get the most. However, if we get much bigger condensed plasmoids, then it keeps on fusing other elements, adding up to tungsten, which is useless for us from energy production-wise. Of course, in an academic viewpoint, it could be of interest. But I mean, anything, of course, anything above iron, to synthesize iron, consumes energy. And this is not yielding energy. So for us, a homogeneous population of condensed plasmoid is the favorite, and small ones, not big one. So small is beautiful in our experiments. But it requires know-how and technology and quality control how to make them. And this is, again, a problem with us, that most of the power, in our opinion, is just leaving the tube as electromagnetic radiation, but most probably not the textbook transversal, but the Tesla type, longitudinal type of radiation. And a neon tube is easy to capture it. I don't know how much time I have.
Well, we are late anyway, so.
Okay. So, of course, we have severe restriction with our budget. We cannot use very high voltage, and we are unable to gauge how much energy can neon tubes detect or absorb. And most of our digital equipment were destroyed during the experiments because these voltage bursts are really dangerous. Let me show you during the test one kind of small reactor. And we have some hints how to improve power output, though I don't think that we shall have enough budget in my lifetime to do it. But this is one reason we should like to spread this knowledge. Those who are much better in attracting funding should go ahead. But I know that I have maybe 5 to 10 years of lifetime, but not much more, so I would rather leave it to a younger generation. So, my usual slogan, change is inevitable, but progress is optional. Thank you for your attention. And as time runs out, I have several videos about the working device, but anyone who is interested, I can show it on my phone. And because this is a very crude device, I can show you maybe during the lunch break or whatever. Thank you.
Thank you again. So we are really 30 minutes late, so, you know, and there are probably dozens of questions, so you are going to have a busy day with everybody sticking to you.
No questions.
No questions.
No questions.
I have a question.
Oh, Anatoly. Yeah.
Hi. It's a very interesting report and many questions. One of them. It's well known that continuous regime is not good. You have relaxation oscillation regime.
Yes.
And the main unit in your reactor is discharge camera with vapor mixture of the vapor and dust particles. Is that correct?
So ideally, we use wet hydrogen. Wet hydrogen is our fuel, but of course it works with wet air, but I don't like because it gives lots of unnecessary transmutation. So wet air, and we use pulsed reactor around 30 kilohertz. So between 5 kilohertz, 30 kilohertz, this is the usual range. The pressure range is between under 0.4 to 0.6 bars, and the usual voltage about 1.5 kilovolts to 2 kilovolts, sometimes 3, but then it is very dangerous because our capacitors, diodes are destroyed. So we are limited with our parameters.
And there is very important negative peculiar feature of your discharge gap connected with the high frequency regime. I hope you never obtain the frequency, repetition frequency up to higher than 1000 hertz. Is that correct or not?
Of course, we use usually in the order of kilohertz, but I would like to know maybe privately why you don't like higher than 1 kilohertz. We are still living, each of my colleagues, so we don't think that it is dangerous to have to go anything above 1 kilohertz. What we really strive for, that we should have this phenomena at the minimum input energy. So very, very small sparks, very small, just less than 1 millimeter diameter sparks.
And the last question connected with your device, with your reactor, you can you should to realize calibration of your reactor with you have a colorimetric measurements, and your measure of COP is not understood because of need to measure heat losses in your reactor.
Because we had a 1-hour lecture at this Chechen meeting by Sebastian Domoslai, so I didn't want to talk and to repeat because I knew that I have 25 minutes. So I had to refer to my previous presentations, so please check it. Okay. It is it's public.
If it is possible to send me, please send me your previous presentation. Okay?
Yes. It's open access because this Chechen meeting is on YouTube and openly accessible, I presume. And the California presentation is all ICCF 24. It's openly available for anyone interested.
Thank you.
Yes, they will be available in a few days, weeks, it depends, but there will be, and at the end they will be available. So thank you very much.